6.2 is a section dedicated to setting up integrals in 3 different types of applications. One is volume, to find the volume of a 3-dimensional region. The second is density, we would integrate the density, find the mass of a rod or the total population living in some area. And the third is average value. So we have some function and some interval, and we're trying to say, on average, what's the value of the function over that interval? So we'll look at each one of these 3 concepts in turn. We'll start off by looking at volume. So for volume, the running example that we're going to be thinking about is that we have some 3D region here. So I've drawn circles here. You should imagine, it almost looks like some kind of vase here. Our question here is we want to find the volume that's inside this vase. And as for axes, we're thinking that the vertical axis here is going to be the y-axis, the horizontal is the x-axis. And so something that's important here is that the horizontal slices, like if we were to slice this 3D region right here, we'd get a circle. That's what I'm intending to have happen with this picture. We slice this right here, we get a bigger circle. And we slice this down here, we get an even larger circle. And so the idea is for each of these circles, or it could be more general shapes, we'll do more general shapes later on, we know what the area is of the cross-section if we cut it at any y value. Okay, so this is the first part. So this is what we're given. We're given the area, we're given the areas as a function of y, of all the cross-sections with respect to y, and we're given some bounds on how far y ranges. Maybe this is y from 1 to 7, or something like that. And so we want to figure out what is the volume here. In order to do that, so if you go back to the title slides, this is promising that we can do that with integrals. So we'll get an integral eventually, but first, we're going to take a small little thin cylindrical slab here. And so the lower value of y here, we'll call this y1. The upper value of y is y2. And in between, we'll talk about y bar, the average of those 2 values, which y bar would be y1 plus y2 divided by 2 here. Okay, so this is our setup. We're thinking about what's going on for this little slab, and realize that this slab is a 3-dimensional thing with very, very thin height here. We're thinking of y2 and y1 as close together, and so we want to talk about what's the volume of this slab. And we might not be able to calculate it out exactly, but we can estimate it by, it's roughly speaking, the area of the cross-section at the midpoint, that plug in the midpoint here into the area function, times the difference in the heights, y2 minus y1. Okay, so this is our this is our volume, and what we're going to think about is that we're going to add up these volumes. We're going to add up these volumes for lots and lots of different values of y, from up here to down here to up here. And when we add in all of these, and when we add up all of these little volumes, so these little slabs, adding up lots of little, really small things, that starts sounding like an integral. And so what's going on here is that we'll end up replacing y2 minus y1 with dy as an arbitrarily small number. Of course, we're already approximating the cross-section with the cross-section at the midpoint. And so what we have then is a little chunk of the volume, dv, is a of y bar times dy. And so if we want to find the total volume, we would have v is the integral over dv of, and we can rewrite that, replace it with integrating with respect to y. A sub y, I'm replacing y bar with y here. And a and b, that was like the 1 and the 7 I was talking about earlier here. And so putting all of this together, here is our first, big statement of this section. So volume as the integral of cross-sectional area. So suppose that we have a of y, we have some function that's known as the area of the horizontal cross-section at height y of a solid body extending from y equals a to y equals b. Then the volume of the solid body is exactly that integral that we saw before. The integral from a to b, the bottom to the top of the cross-sectional area integrated with respect to y. And so in future videos in this section, we'll do some examples here. Some of them will be, the cross-sections will be perpendicular to different axes, so we'll do several different examples. But that's the setup here for these problems.